Earlier, I totally forgot to record this meeting. Now it's already in recorded form. Good thing that I have not done a big full example yet. So for those people who rely on lecture video, it seems like the first half of this lecture, you can look at the notes, and starting from example 5, then you can see this how to apply those theories that we learned earlier. Okay, let's start. I will factor these rational functions. I will get x minus 4, x plus 1, and on the denominator we have common factor 2. Is it right?
Yes.
And then factor further, I get x plus 2, x minus 2. So the domain will be all real numbers except 2 and negative 2. The y-intercept will be 0,
1/2.
half. That's right. How about the x-intercept?
4,0.
4, 0, and then
Negative
negative 1,
1,
0. That's right. How about the vertical asymptote?
x equals to negative 2x equals to 2.
That's right. Oops, I almost used coordinate. That's right. X equals to 2 and x equals to negative 2. Now, how about the horizontal asymptote?
Y is equal to 1/2.
Y equals to 1/2. Okay. Now let's do a sign graph before we do the graphing. So part F, the sign graph. Negative 2, negative 1, 2, 4. This is 0 here, this is 0 here, undefined here, undefined here. The y-intercept is positive, so this is positive. All the zeros are simple zero, multiplicity of 1. So every time I jump across the critical number, I change the sign. Therefore, when I graph this, oops, too much. I need the sign graph. Let me do it here. So I have this, let's say this is my graphing paper. 0, 0,1/2 is here. 4, 0 is here. So extend this would be, and then another x-intercept negative 1, 0. Vertical asymptote x equals to 2. X equals to negative 2. And the horizontal asymptote y equals to 1/2. Oh, exactly here. Huh? Y equals to 1/2. Now again, what happened to the graph? Between negative infinity to negative 2 it's positive, so it's from horizontal asymptotes, and it will go up here, right? It won't go down because that way we will get an extra x-intercept and a change of sign here, which is not what we see from our sign graph. And then between negative 2 and negative 1, it's below x-axis. Between negative 1 to 2, it's positive above x-axis. And oh, I have x-intercept here. Huh? I think I marked it earlier, but it's bigger. Now then, Between 2 to 4 is below x-axis because it's negative. And between 4 to infinity, it's positive, but we have a horizontal asymptote there, so it will go very, very close. So I hope you see how the sign graph actually helps us in graphing this. Now, let's deal with the one with holes, for example. Example 6. Let's say let Rx equals to, what did we have earlier? I want to copy paste that. Let me just use this one. Sorry. But this time I will change the 8 becomes 2. Which then factor to be x minus 4, x plus 1 over 2 times x plus 1, x minus 1. Then from here we see that the domain is, let me go a bit to the left. The domain is all real numbers except negative 1 and 1. Part B, the y-intercept is, what's the y-intercept?
Zero comma 2.
0,2. How about the x-intercept?
Four comma 0 and negative 1 comma 0.
4, 0 and negative
Negative
1,
1.
0. Is it okay, everybody? Is it okay, everybody? The answer is not really okay. Something not really right. We need to avoid this guy here. You see this? Right? Negative 1 is not in the domain. So we have to avoid that one. Now, how about the vertical asymptote? Vertical asymptote, we will look at the simplified version. You see something cancel, right? So we have x minus 4 over 2 times x minus 1. So the vertical asymptote will be x equals to 1 only. Now, remember, if we have this kind of situation, here, x plus 1 cancels. It means in the graph later on, x equals to -1 will be undefined, but not vertical asymptote, not x-intercept. Okay? How about the horizontal asymptote?
One half. Y is equal to that, 1/2.
Now let's see what happened to the sign graph. We have -1, 1, and 4 as critical numbers. 4 give us zeros, 1 give us undefined, and -1 also give us undefined, but later on, this x equals to -1 we know will be a whole. That's why we still call that undefined, but when it comes to graph, instead of becoming a vertical asymptote, it is actually a whole. Now let's put them in graph. Y-intercept 0, 2, x-intercept 4, 0. 0, 2, x-intercept 4, 0. Vertical asymptote, x equals to 1. Horizontal asymptote, y equals to 1/2. And from the sign graph, we see that oh, I'm not done with my sign graph yet. I'm sorry. My y-intercept is 0, 2, so this is positive here. The multiplicity of -1 is multiplicity for x equals to -1 is 2 because it happens once on the top, happens once at the bottom. It's twice, so this is still positive. The multiplicity of x equals to 1 as a 0 is 1, so it's odd, so we change sign. For 4, also multiplicity of 1, we change sign. Then what happened is, from -infinity up to 1, it will be positive. Okay, but don't forget, at -1, at x equals to -1, we have a whole. So let me erase this. We have a whole. We have a whole here, and then go on. And then to the right of x equals to 1, between 1 to 4 it's below x-axis, between 4 to infinity is above. You can compare with your sign graph. Okay. Now from here, there are actually two issues that I need to go on. So we are into the variation problem already. Some big questions. First big question, how do we find what is the coordinate of the whole? Now we know that the whole happen at, in this case, x equals to -1, right? Now, to find the y component, do not put it into the original function, because when you plug in x equals to 1 here, you will get 0/0. Okay, I mean x equals to -1. When you plug in x equals to -1, you'll get something over 0, which is undefined, right? Okay, now so you will get 0/0. Now what you will do, you plug into the simplified version of the function. So if I want to find what is the coordinate of the whole, then it would be r star -1 equals to, what's that again? X minus 4, 2 times x minus 1. So that will be x minus 4, 2 times x minus 1. That's -5 over -4. That's 5 over 4. Therefore, the coordinate of the whole is -1, 5 over 4, slightly above y equals to 1. So if this is y equals to 1, then the whole is between y equals to 1 to y equals to 2. Okay, now that's the coordinate of the whole. Now the second issue is if the graph crosses the horizontal asymptote. Now, let me say this. The graph will never cross vertical asymptote. The graph will never cross the vertical asymptotes, okay? Because vertical asymptotes is from the denominator, it will give us undefined, right? So the graph will not cross vertical asymptote. But it is possible the graph cross horizontal asymptote. Now,
Thomas,
how do we know?
You're really breaking up. Your audio is.
Oh, I'm sorry.
Can you do something with Mike?
Okay, let me say it again. The graph will never cross vertical asymptote. Because when we plug in the number not in the domain into the function, we'll get undefined. However, the graph may cross horizontal asymptote. Now then, how do we find the coordinate if the graph cross horizontal asymptote? Where will that be? Now, it seems like the way I graphed that earlier above here, I didn't anticipate that, but let's take a look. Let's take a look. How do we find the intersection? Now, the way is the following. We will set the function Rx, or maybe R star X. We set that to be equal to the horizontal asymptote. And then we solve for the X. Now, the simplified version here is X minus 4 over 2 times X minus 1. And what is the horizontal asymptote again?
Y is equal to 1/2.
Y equals to 1/2. So I replace this horizontal asymptotes becomes the y equals to 1/2. Then I will try to solve this. In this case, I will do cross multiply 2 times x minus 4 equals to 2 times x minus 1. So 2x minus 8 equals to 2x minus 2. Cancel the 2x, I get -8 equals to -2. That's a contradiction. Therefore, in this case, there is no horizontal asymptote intercept. In other words, the graph does not intersect horizontal asymptote. Now, we may have a case later on that the graph actually cross horizontal asymptote. Okay, you can see problems from my old tests where we have those kind of cases. Now, because of the time, let me go on further to another variation. I think this is the last variation, something called oblique asymptote. Oblique asymptote. Or in the past, we call that slant asymptote. In fact, I would still call that slant asymptote simply because of the nature that it is actually slanted. It's not horizontal, it's not vertical. Let's take a look on an example where we have a slant asymptote situation. Let me go to my graphing paper, graphing software. Let's say I have y equals to x squared minus 4 over 2x plus 3. You see that instead of the graph going to the left and to the right horizontally, it is actually getting closer to this line here. It gets closer to, seems like we have a line from this side going to that side. Now that line, let me copy this, copy graph, and then put it on our. Okay, now I put it on our notes. Now notice that it seems like the graph, when it goes to very far to the left, it gets closer to this line here. There's the line that it gets closer here, and there's a line that it gets closer on the far right. Now, this is what we call slant asymptote. It's slanted because it's not vertical, it's not horizontal. Now, under what situation we have slant asymptote? Slant asymptote is a line to which the graph of Rx gets closer to as x goes to positive or negative infinity, and the line is not horizontal. Okay, now that's the definition of slant asymptote. Now, how to find slant asymptote? By the way, are we on the node view or still the graphing view?
We're on the note. You're good.
Okay, thank you. So, how do we know that we have slant asymptote or not? We have, or the graph have slant asymptote. I will denote that by SA if the degree on the top is exactly one more than the degree at the bottom. if the degree on the top is 1 more than the degree at the bottom. Now, if you take a look on the example we have here, oh, what's the function I use? This was y equals to x squared minus 4 over 2x minus 3, I believe, or plus 3. Let me check. Plus 3. Now you see the degree on the top is 2, and the degree at the bottom is exactly 1 less than that. Then the question is, then Thomas, how do we find the equation of that slant asymptote? You see, it's a line, so we must have an equation for that. Now, how to find that equation? Now, to find the equation, we divide the rational function. Like in this case, for example, we have Rx equals to x squared minus 4 over 2x plus 3. Then we do long division, or if you can use synthetic division, go for it. So x squared plus 0x minus 4 divided by 2x plus 3. Remember, I think on last week, I told you to know how to do long division. This is where it comes into play. Now 2x times what gives us x squared? Anybody can help?
1/2 x.
1/2 x, that's right. We need 1/2 x. So it's 1/2 x. Distribute to 2x, give me x squared as we expect. Distribute to 3, I get 3/2 x. And then we subtract, I will get negative 3/2 x minus 4. Now then we repeat the procedure again. 2x times what give me negative 3/2 x. There should be a negative, huh? There should be a negative to change the sign, right? I need to have a 3, but divided by 4. Okay, so I will have minus 3/4 here to get negative 3/2 x minus 9 over 4. Now, I actually don't worry about this because what I need is this guy. Okay, so the slant asymptote will be y equals to 1/2 x minus 3/4. Now, we for sure will have this linear equation for our slant asymptote because the degree of the numerator is exactly 1 more than the degree of the denominator. The degree of the numerator here is 1 more than the degree of the denominator. Therefore, when we divide, we must have a linear function as the quotient. Okay. Now let's see a problem from our book. For example, let me read question number 38. We have fx equals to 2x squared minus x minus 3 over x minus 2. If I factor the top, I get 2x. I think it's minus 1. No, I think it should be minus 3. Minus 3 and then plus 1. And then I get x minus 2. The reason I factor it so that we can easily find the domain, which is all real numbers except 2. The y-intercept 0, 3/2. I hope I'm not too fast here. We did this many times already, right? And x-intercepts, I get 3/2, 0 and negative 1, 0. And then the vertical asymptote, x equals to 2. Horizontal asymptote, there's none. Because n, which is 2, is greater than n, which is 1. The degree on the top is more than the degree at the bottom, so there's no horizontal asymptote. Okay, now, but because the degree on the top is exactly 1 more than the degree of the denominator, then we must have a slant asymptote. Right? Notice that the degree on the top, which is 2, is equal to the degree of the bottom plus 1. Right? Okay, so we must have slant asymptote. Now, how to find this as slant asymptote? We will divide the numerator by denominator. Everybody with me? Now, the nice thing is the denominator happens to be in x minus c form, so I can just use syntactic division. So the slant asymptote is y equals to 2x plus 3. Where I get the 2x plus 3? From here. Okay, you may want to write it down first before I proceed with the graphing. Okay, let's go with the graphing. I need the information above, so let me see. Oops. So the y-intercept 0, 1.5. The x-intercepts are 1.5, 0 and negative 1, 0. Vertical asymptote x equals to 2. Oh wow, sorry. No, this is not big enough. I need to go down further. Sorry. I need a larger space. It's the y-intercept. is one of the x-intercept. Another x-intercept. And then I have vertical asymptote y equals to, x equals to 2. I don't have horizontal asymptote, but I have slant asymptote y equals to 2x plus 3. So the graph actually for the slant asymptote is this. The slope is 2, but the y-intercept is 0, 3. So approximately like this. Now then, what the graph look like? I didn't do the sine graph, but you can see that I will start from the slant asymptote going. Oops, I will start from the slant asymptote going this way. Sorry. And later on, we have something up there here too. Okay. Now, in case if we want to find slant asymptote intercept, the coordinate where the graph intersect the slant asymptote, what we can do is we set the slant asymptote, which is what? What is the slant asymptote again? 2x plus 3. To be equals to the function. What's the function? 2x squared minus x minus 3. 2x squared minus x minus 3 over x minus 2. And then we solve for x. Let's see if any. I don't think so though, but you never know. When I FOIL this, I get 2x squared minus x minus 6 equals to 2x squared minus x minus 3. I get negative x equals to negative 3, which is a contradiction. So no slant asymptote intercept. Okay, that's the graph. Now let's take a look on the actual graph using my graphing software. Y equals to, what was that? 2x squared minus x minus 3 divided by x minus 2. Am I right?
Yes.
So this is what the graph looks like. If I zoom it out, that's what it looks like. Now, if you want to see the slant asymptote better, let me put it here. I believe that was y equals to 2x plus 3, huh? So the red color is the slant asymptote. And the purple color, you see from the colors here, right? The purple color is the graph that we look for, and the red color is the slant asymptote. And you see that The further we go to negative infinity, the closer the graph to the slant asymptote. The further we go to positive infinity, the closer the graph to the slant asymptote also. Sorry, I have a question here. I just saw it. Why isn't x equals to 0 positive? When x equals to 0, y is not positive. I think it is positive. It is not. It is positive. It's above x-axis. Yes, it is below the slant asymptote. It's below the slant asymptote, but it's still positive. According to our computation earlier, it's supposed to be 0.3 right? When x equals to 0, the y is 3/2. Oh, the question from example 6. Let me take a look on the paper again. Give me a second. Sorry, I didn't see that earlier. Example 6. This is example 6. The y-intercept is 0.2. So it is positive. It is positive. This is the graph. This is the graph. Okay, this is the graph for that example 6. I think if we look at this one, this is another example. And here, on the sine graph, y is a little positive. Is it right? It is positive. When x equals to 0, it is positive. Oh, okay, now let's continue. So this is how we get that slant asymptote. You basically divided the numerator by the denominator. If we are lucky, we can use synthetic division in our example number 38. But if we are not so lucky, then we need to use long division. Basically, we divide it. Okay. Now, last part of today's lesson will be a little further detail. The following is something I don't really ask. Actually, I don't think I will ever ask this type of question. But this question actually show up in our textbook. Something called curvilinear asymptote. Curvilinear asymptote. Which is a strange terminology because the word curve means it's not linear, right? You see that this is actually a contradictory statement in one word. Well, anyway, we try to understand what this means. Notice that when we did the far end behavior, we have either horizontal asymptote or slant asymptote. Now, horizontal asymptote, y equals to 0 if the degree on the top is less than the degree of the bottom. equals to the constant term over the constant term if the degree at the top equals to the degree of the bottom. Now, what happens if the degree is on the top is more? Then we say if the degree on the top is only one more than the degree at the bottom, then we have slant asymptote. Now, what happens if it is even more? Let's say the degree on the top is more than n plus 1, the degree at the bottom plus 1, even more than that. Then that's the time we will get curvilinear asymptote. Okay, now, but how do we get that? And what it means? I will do it the following way. I will pick example from the book. So not only we know how to find it, we also know what to do. For example, I use question number 42. We have fx equals to x to the x to the 5th minus x cubed, sorry, 3x cubed minus x squared plus 1 big over x squared minus 3. And the question is find the curvilinear asymptote. I would just go ahead with curvilinear asymptote. You can find the domain, the x-intercept, y-intercept yourself, vertical asymptote, so on and so forth. But how to find the curvilinear asymptote, I basically divide. So x to the 5th plus 0x to the 4th minus 3x cubed minus x squared plus 1 divided by x squared minus 3. Now, x squared times what give me x to the 5th? X squared times what give me x to the 5th? That's right, it's x cubed. So that's x cubed. Let me erase this. X cubed, and then I distribute this x cubed. I get x to the 5th minus 3x cubed. Then I subtract. I get 0 here, I get 0 here, I get 0 here, I get negative x squared plus 1. So this is minus 1 or negative x squared plus 3. I don't worry about this anymore, but then I get my curvilinear asymptote will be y equals to x cubed minus 1. Now, to show you what the graph look like, so that you understand what's curvilinear asymptote look like, let's take a look on the graph. That will be x to the 5th minus 3x minus 3x cubed minus x squared plus 1 all over x squared minus 3. This is what the graph looks like. Wow, it's so ugly, huh? Ooh, my bad. I try to help you visualizing it, but it seems like it's an ugly graph. Let's see, this is what it looks like. To the left of negative 2, actually, to the left of negative radical 3, it looks like this, while to the right of that, it looks like this. Now, what is curvilinear asymptote? Curvilinear asymptote. What is my curvilinear asymptote again?
X cubed minus 1.
Y equals to x cubed minus 1. Now you see, in between they are not coincide though, but if we go further to the left, for example, you see it gets closer to the red curve, right? Closer to the red curve. Now the red curve is what we call the curvilinear asymptote. So the further it goes to the left or the further it goes to the right, then the graph gets closer to x cubed minus 1. I hope you can see that. Okay, now the reason looks so weird. Yes, that's right. The line looks so crooked. That's why I hope now you understand why I never asked this question. Even if I ask this type of question, I will only ask you, oh, what's the curvilinear asymptote? But in reality, it's so hard to graph, you know, so I don't worry about this. Now, let's go back to the notes. I want to write down the suggested homework you can do from the book. And make sure that you come back to this, the discussion main board, because I also want to show you which question you can do from my old test. Okay, from 3.5, the suggested homework will be from number 3 to number 49. Number 3 to number 49. Just do every other odd. Just do every other odd. Okay, and of course, feel free to ask me questions if you have any. On Wednesday, I will do 3.6 and 4.1, maybe with 4.2.
Do we no homework from 3.4?
From 3.4, I didn't assign anything from 3.4.
Not that I'm aware of.
Oh, I think I assigned from number 19 to 29. Let me write it down. So from 3.4, the one from last Wednesday, right?
Yeah, from 19 to 29.
Yeah, I think I assigned 19 to 29.
Okay, I'm behind. Thank you.
No problem. Okay, then see you on Wednesday. Actually, once we're done with this, you can do plenty of problems. A big portion of your from my old test too, because the main big issue in my test two is actually polynomial and rational functions. We will have a little bit about inverse function, exponential function, so on and so forth. But for now, you can do at least half of my old test two already. Okay then, so long. See you on Wednesday.
Goodbye.
Bye-bye.
Bye-bye.